Network architecture. This involves sensor network scenarios, receiver design consideration, optimization goals, and figures of merit. The first one is the network architecture. It introduces the basic principles of turning individual sensor nodes into wireless sensor network. This involves sensor network scenarios, transceiver design consideration, optimization goal, and figures of merit. The sensor network scenarios are classified into types of sources and sinks, single hop versus multi-hop network, multiple sink and sources, three types of mobility. Optimization goals and figures of merit are classified into quality of service, energy efficiency, scalability, robustness. Sensor network scenarios, types of sources and sink. Source is any unit in the network that can provide information. A sink is the unit where information is required. It could belong to sensor network or outside this network to interact with another network or a gateway to another larger internet. Sinks are illustrated by the figure, showing source and sink in direct communication. Here shown is three types of sink in very simple single hop sensor network. Single hop versus multi-hop networks. Because of limited distance, the direct communication between source and sink is not always possible. In wireless sensor network, to cover a lot of environment, the data packets take multiple hops from source to sink. To overcome such limited distance, it is better to use relay stations. The data packets taking multiple hops from source to sink are shown in the figure. Depending on the particular application of having an intermediate sensor node at the right place is high. The figure shows multi-hop network as direct communication is impossible because of distance or obstacles. Multi-hopping also improves the energy efficiency of communication as it consumes less energy to use relay instead of direct communication. The radiated energy required for direct communication over the distance, which is represented as D, is CDA, where C represents the constant, D represents distance, and A represents the path loss coefficient. It can also be written as alpha. And using a relay at distance d by 2 reduces this energy to 2c d by 2 alpha. This calculation considers only the radiated energy. It should be pointed out that only multi-hop network operating in a store and forward fashion are considered here. In such a network, a node has to correctly receive a packet before it can forward it somewhere. Multiple source and sink. In many cases, multiple sources and multiple sinks are present. Multiple sources should send information to multiple sinks. Sinks are nothing but the destination node. Either all or some of the information has to reach all or some of the sink or destination. This is shown in the figure. Multiple source and multiple sinks, as you see. Three types of mobility. In the scenario discussed so far, all participants were stationary, but one of the main virtues of wireless communication is its ability to support mobile participants. In wireless sensor network, mobility can appear in three main forms: node mobility, sink mobility, and event mobility. Node mobility. The wireless sensor node themselves can be mobile. The meaning of such mobility is highly application dependent. In examples like environmental control, node mobility should not happen. In livestock surveillance, where sensor nodes attached to cattle, take this as an example, it is a common rule. In the phase of node mobility, the network has to recognize to function correctly. Then is the sync mobility. The information syncs can be mobile. For example, a human user requested information via PDA while walking in an intelligent building is shown in the figure. In a simple case, such a requester can interact with wireless sensor network at one point and complete its instruction before moving on. In many cases, consecutive instructions can be treated as separate, unrelated requests. The figure shows the sync mobility. The mobile sync moves through a sensor network as information is being retrieved on its behalf. Then is the event mobility. In tracking applications, the cause of the event or the object to be tracked can be mobile. In such scenario, it is usually important that the observed event is covered by a sufficient number of sensors at all time. As the event source moves through the network, it is accompanied by an area of activity within the network. This has been called the Frisbee model. The notion is described in the figure where the task is to detect a moving elephant and to observe it as it moves around. The figure shows the area of sensor nodes detecting an event, that is, an elephant that moves through the network along with the event source. Transceiver design considerations. Some of the most crucial points influencing physical design in wireless sensor networks are low power consumption. As one consequence, small transmit power and thus a small transmission range. As a further consequence, low duty cycle. Most hardware should be switched off or operated in a low power standby mode most of the time. Comparably low data rates on order of 10 to 100 kilobits per second is required. Low implementation complexity and cost, low degree of mobility, and finally, a small form factor for the overall node is considered. Optimization goals and figures of merit. For all wireless sensor network scenario and application types have faced the challenges such as how to optimize a network, how to compare these solutions, how to decide which approach is better, how to turn relatively inaccurate optimization goals into measurable figures of merit. For all the above questions, the general solution is obtained from quality of service, energy efficiency, scalability, and finally robustness. Quality of service. Wireless sensor network differs from other conventional communication networks in the type of service they offer. These networks essentially only move bits from one place to another. Some generic possibilities are event detection or reporting probability, which means the probability that an event that actually occurred is not detected or not reported to an information sink that is interested in such an event. For example, not reporting a fire alarm to surveillance station would be a severe shortcoming. The next is the event classification error. If events are not only to be detected but also to be classified, the error in classification must be small. Event detection delay. It is a delay between detecting an event and reporting it to any or all interested sink. Missing report. In applications that require periodic reporting, the probability of undelivered report should be small. Approximate accuracy. For function approximation application, the average or maximum absolute or relative error with respect to the actual function. Tracking accuracy. It is the tracking application that must not miss an object that is to be tracked. The reported position should be as close to the real position as possible, and the error should be small. So these are the quality of service. Energy efficiency. Energy efficiency should be optimization goal. The most commonly considered aspects are energy per correctly received bit, energy per reported event, delay or energy trade-off, network lifetime, time to first node death, network half-life, time to partition, time to loss of coverage, time to failure of first event notification. Energy per correctly received bits is how much energy is spent on average to transport one bit of information from the transmitter to the receiver. Energy per reported event is what is the energy spent to report one event. Delay or energy trade-off is the urgent events increases energy investment for a speedy reporting event. Here, the trade-off between delay and energy overhead is interesting. Network lifetime. It is a time for which the network is operational. Time to first node death is when the first node in the network runs out of energy or fail and stop operating. Network half-lifetime is when we have 50% of node run out of energy and stops operating. Time to partition is when the first partition of the network into two or more disconnected parts occur. Time to loss of coverage, the time when for the first time any spot on the deployment region is no longer covered by any node's observation. Time to failure of first event notification is a network partition that can be seen as irrelevant if the unreachable part of the network does not want to report any events in the first place. The scalability. The ability to maintain performance characteristics irrespective of the size of network is referred to as scalability. When wireless sensor network potentially consists of thousands of nodes, scalability is an obviously essential requirement. The need for extreme scalability has direct consequences or result for the protocol design. Often, a penalty in performance or complexity has to be paid for small network. The architecture and protocol should implement appropriate scalability support rather than trying to be as scalable as possible. Applications with a few dozen nodes might admit more efficient solution than application with thousands of nodes. Robustness. Robustness is the property of being strong and healthy in a constitution. When it transponds into a system, it refers to the ability of tolerating perturbation that might affect the system's functional body. It is basically to be strong and to be in good condition. The ability to withstand or overcome adverse condition is called robustness. Wireless sensor network should also exhibit an appropriate robustness. They should not fail just because a limited number of nodes run out of energy or because their environment changes and severe existing radio links between the two nodes. If possible, these failures have to be compensated by finding other routes. Two diagrams are seen here. The first one is the star topology and the other mesh. In the star topology, there is only one link that has been connected with the center node, whereas in the second, we see that there are multiple possibilities of sending the data. So even if one gets disconnected, we can go on with the other route. So this is more reliable for being robust.